So design aggregate structure. So you guys have just finished up the portion where we select materials. We've tested the materials. Now we've got to figure out how do we blend these materials together, how do we come up with some trial blend designs that we can get gradations on and figure out what we're going to actually use for our design. So one of the most important things that you need to learn when doing a super pave mix design is about the Power 45 chart developed by the FHWA. We're going to talk about control points. We're going to talk about combining aggregates for each of our blends. We're going to talk about our trial blends, and we're going to select the design aggregate structure that works best for us. Here's an example of a batch of trial blends. You can see this can have anything from our coarsest material like a 57 or a 68 down to kind of an intermediate size material. We've got some manufactured sands in there, some natural sands as well. So this is a typical Power 45 chart. We're going to talk a lot about this, and this chart is basically a graph, a plot of your gradations on a graph. And this line here, this yellow line, is called your maximum density line, and this basically runs from the intersection of this axis, this axis here that's running from 0 to 100, that's your percent passing on your gradation. And this axis here represents your sieves. Your finest sieve down here at the bottom would be your 200 sieve, all the way up to your 2-inch on this end. Basically anything on this side of the curve would be considered a coarse graded mix. Anything on the low side of the line would be considered a fine graded mix. These are our control points. We're going to talk about those as well. These are basically the range of gradation where you're allowed to design your mix in. And this is called the restricted zone. We're going to talk about that here in a bit too. Two definitions that you really need to know. Very important you know this for the exam. Also very important that you know this so you can make your own chart. The nominal maximum sieve size is one standard sieve size larger than the first sieve to retain more than 10%. It's not the first sieve to retain more than 10%. It's the first sieve size larger than the first to retain 10% or more. It's very important to know. The maximum sieve size is one standard sieve size larger than the nominal max. And that's the line, the maximum sieve size is where our maximum density line is drawn to. So what are standard sieves in super pave? As you notice, all of our standard sieves are in metric. Basically, we're starting here at the 50. That's the 2-inch. The 37.5 millimeter is 1.5 inches. The 25 millimeter is 1 inch. The 19 millimeter is 3/4, and so on, all the way down to the 0.075 micrometer, which is your 200 sieve. The reason this is important, if standard sieves aren't used, then it's truly not a super pave mix design. The pharmaceutical industry, there are lots of industries that use sieve nests just like we do that have different sizes. So you can't use a 3/16 or a 1/4 or a 5/16. They've got to be these same sieve sizes. They've got to be these metric units before you can use them for a super pave mix design. So the gradation criteria on a Power 45 chart, we have control points, which are the maximum size of the material, the nominal maximal size, and then also the gradation parameters of our mix design. So they mentioned key sieves here, and in a lot of cases they mentioned the 200 and the 8. In a lot of cases the 30 is a key sieve, the 3/8, the half, and so on. There's also a recommended restricted or warning zone. This is no longer used by VDOT. When super pave first started in around 2000, it was recommended when we did designs that we would do a design above the restricted zone, through the restricted zone, and below the restricted zone. And basically the department was trying to gather data and try to see how different mixes behaved in design in the lab and utilizing a couple of different blends. The restricted zone was meant to be a kind of a warning area that this mix could be potentially a ruttable mix or a tender mix if it went through the restricted zone. What we found over the years most of the mixes that were working very well, most of the best mixes that were out there ran right through the restricted zone. So it's not even, it's still on a lot of the software. We keep it and teach it mainly for the history portion of the class, but it's not something you have to worry about if you've got a mix running through the restricted zone. Really not an issue. It's not a specification. So this is a 19 millimeter mix, so an IM 19.0. These are the parameters. We've got 100% passing. The 1 inch got to be between 90 and 100 on the 3/4, maximum of 90 on the half, between 28 and 49 on the 8, and between 2 and 8 on the 200 sieve. So basically the blend of our materials for our trial blend has to run through these wickets. This is basically the recipe for an IM 19 mix. And if you're looking on your software, you'll see that they have the restricted warning zone area, so you know how to build that if you were to write one up and do it yourself. So here's that same IM 19 mix. This has got the, you can see the maximum density line is going up here, and at the inch we're 100% passing, which is where we're starting. Here's our 3/4 where we've got to be 90 to 100. Here's our 28 to 49 at the 8 sieve, and here's our 2 to 10 or 2 to 8 on our 200 sieve. So basically our design is going to have to run through these wickets for it to be acceptable. So here's trial blend number 1, and it comes through, and if you notice, there's a couple of things that you need to notice about this. The wickets basically up here at the top at the 3/4 are above the maximum density line. If you notice down here for the dust, we're below the maximum density line. One of the reasons for that is when an engineer looks at your Power 45 chart, he uses that as a gauge to determine how that mix is going to behave. This maximum density line is really representative of, if your gradation ran perfectly along that maximum density line, that would be to say that you have a perfectly homogeneous distribution of material from the top all the way down to the bottom. And if that were true, you could potentially have basically a mixture of materials that's almost fluid, and it would be potentially not a lot of void space in it. And it could be have a lot of rut potential. So when an engineer looks at this, if he sees a mix that's running right along that line, that's going to probably throw up some red flags. It's for that reason that the department designs their mixes with these ranges off of the line. So as you can see here, by putting the wickets up here, they're pulling our design off of that line. Then it comes down and crosses, kind of runs along it, stays on the low side. What we're doing here is making sure there are gaps in the mix so this stuff locks in together really well and doesn't create a mixture that's fluid. So this is the first one that actually runs on the low side of the restricted zone. Here's one that's even coarser. So if you notice, this one drops down even lower than blend 1 on the low side. We would consider these coarse graded mixes. They're on the coarse side of the line. Again, the coarser you get in your mix, remember this is our percent pass in our sieves over here on the left side. The coarser your mix is, the more these lines are going to want to favor this side. And here's trial blend number 3, which is running on the fine side of the maximum density line. And this would be considered a fine graded mix. These are kind of exaggerated so that you can see all of these would be passing to submit as a VDOT mix design for an IM 19.0 mixture. So here's the actual design that we're utilizing. This is the SM125. Here's our blend 1, which is a virgin mix design that's running up on the high side. Blend 2 is this blue line here. That one's got 10% wrap in it, and it's got I think that's a fully manufactured sand material. There's no natural sand in this one. And then running right through the middle is our blend 3. That's a 25% wrap design. And as you can see, this one's been pulled off the line. That's, our engineers at VDOT understand that, and that's why they've pulled these designs off of it, to get it off of the line so that when these materials go together in a mixture, they lock together well. Here are our blends. As you can see, trial blend number 1, this tells you exactly how much each of these individual aggregates, what the blends are composed of. Again, one of the neat things with mixed designs, you have a lot of room to move and do creative things with your design. Again, you saw with that IM Power 45, you can be sort of along a wide range of area that you can play with these blends. So trial blend 1, we've got no wrap in it. It's coming out the same plant. That's why you only see 1% for each of these. That's the breakdown that we anticipate happening at the asphalt plant. Does have a blend of natural sand and B sand, but it's a pretty fine mix. Blend 2 is we went straight 78s. We didn't put any 8s in it. There's no natural sand, so it's a fully manufactured mix except for the 10% wrap. Trial blend 3 is a high wrap mix. We got 25% wrap in it. We blended some natural sand in with that manufactured sand. Our consensus properties look good. If you notice, here we've got a 44-1, which is less than the 45, so our natural sand is actually failing by itself, but we're able to use it because this manufactured B sand we've got pulls it up as a consensus property. So you can utilize a lot of materials that maybe by themselves you wouldn't be able to utilize, but because it's a consensus spec, you can blend them with other materials and they can still pass. So here are gradations. Again, this is an SM 12.5. You can kind of see the difference here at the 3/8. We're going down from just under 90% down to 83. On the 8 sieve, we're getting a little more. We're pretty fine here, about 49%, down to 36% on blend 2. The dust, again, you can really see how the wrap is affecting that. Here's our virgin mix at 3.8%. This fully manufactured mix with only 10% wrap is at 4.7. And then our blend 3, which is our high wrap, and you would expect it to have more dust than it does at 5.4. So this is the FHWA chart. Again, you really don't need to memorize this, but it's important to know. We teach this because it's part of the requirement for super paved mixed design for VDOT. VDOT specifications kind of spawned from the FHWA specifications. However, if you're doing a work for an airport, for parkway, for a federal job, there are specific specifications for that work. You do need to know those. But this is an FHWA specification on your consensus properties. You can see some of them are a little bit different. There's some 40 here on sand equivalent, a 50. Everything in Virginia stays at 45. So there are some subtle differences there. Here's section 21102, table 2-12A. These are the consensus properties for Virginia that we are currently utilizing. Very important to know, you'll see this quite a bit on your exam, or you'll refer to this. Also, table 214, this is the table that we refer to most often. This is really our cookbook. This is what tells us how we do our designs. Again, be sure to pay attention to the footnotes. Asphalt content should be selected at 4% air voids. That's really why we're doing this SM 12.5 at 4% air voids. That's what we're looking for. There are some subtle differences in these footnotes based on whether it's a base mix or not, and also whether it's an E mix with polymer in it. If you have any questions concerning this section, please refer to your room proctor.